All right, any questions at all? I suspect there's going to be some. Go ahead, Zebby. 2D. So we want to simplify sine squared of pi over 2 minus x plus sine squared of x. That's the one, right? There's no identity for the square of the sine of the difference of two angles. So what we need to do is think of this as being sine of pi over 2 minus x. Now, you know, if I wanted to here, I could put sine of pi over 2 minus x times sine of pi over 2 minus x. But what I'm going to choose to do instead is this. So essentially what I'm saying, everybody, is what we're going to do is apply the difference identity to sine of pi over 2 minus x to see what we get, and then we're going to square the result. This is also plus sine squared of x. So let's see. I'm going by memory here, but I think I have the sine identity for the difference of two angles as being the sine of the first angle multiplied by the cosine of the second angle minus the cosine of the first angle multiplied by the sine of the second angle. How did I do? That's correct. So now, I don't forget, I'm going to be squaring this. I'm just a little curious right now, how many of you see that I believe this is going to work out to 1? Some of you see that already. What's going to happen inside here is sine of pi over 2 is equal to 1, and then we have the cosine of x. No need for the square brackets, I guess. Minus cos of pi over 2 is 0 multiplied by sine of x. So what is in brackets there works out to be just cosine of x, because 0 times sine of x is 0, so you're left with cosine of x in brackets. And then we have, outside of the brackets, we're squaring it, but we also are adding sine squared. What's going to happen here, Zebby, is if this is simply cosine of x, and we're squaring it, then of course we don't write it as cosine of x quantity squared, we write it as cos squared of x. And now we're at a very familiar area. Cos squared plus sine squared is equal to 1. Is that okay? Okay. Other questions? Yeah. 1b. Okay. So we want to figure out what sine of pi over 2 minus x is. We're going to apply, do you see what's going to happen here? I don't want to brush your question away, but sine of pi over 2 minus x happens to be what we did here. Forgetting about the squared, forgetting about the plus sine squared of x afterwards, it is cos of x. So are you okay with me just doing that? Okay. Other questions? Go ahead. Okay. Number 9. This is a very specific type of question that you might see on my exam or the diploma exam. And although there might be a different way for you to do it, and I think we have time today, I might show you the different way. This is the intention of the question. The intention of the question is for you to take cosine of a plus b equals that number and write it as cosine of a cosine of b minus sine of a sine of b, and it's equal to 0.83 0.4320. So all I've done here, everybody, is I've taken cos of A plus B and looked at the identity of cos of A plus B. And I'm pretty sure I have that right, but you will let me know, please, if I got that right. Cos of A plus B is cos A cos B minus sine A sine B. Okay. And then we're going to apply the same idea to the second statement, which is the cosine of A minus B. Well, cosine of A minus B is cos A cos B plus sine A sine B. And this is equal to 0.4358. Does that make sense, those two statements? I mean, not my motivation. My motivation is here because I know what's about to happen, and I've seen this question before. What you are asked to determine the value of is this, which is here. And when you first read this question, I think what most people would say, myself included, the first time I saw this type of question is, I guess I need to find A and B, and you don't ever find A and B. What we can do to this system of equations, I guess is what it is add the two equations. We're not adding them to see if we can figure out what A and B are. We're simply adding them because I see that if I add them, I end up with 2 multiplied by cosine of A multiplied by cosine of B is equal to what I believe is 1.2678. Pretty sure. And then what you're going to end up saying is, since this is the answer to the question, this is what the question is asking us to find, I can just take that 1.2678 and divide by 2. Now, I'm going to show you a different way that will work, and it's a lot of number crunching on your calculator, but it works. And because it's a lot of number crunching, some of you might not follow it, and that's fine. Okay. First of all, you are not told which quadrants angle A and B are in. So apparently it doesn't matter. Let's just say they're in quadrant 1. Okay. So what I am going to do, I don't even think we need to worry about that. What I'm going to do is take this first statement right here, and I'm going to find out what A plus B is. And I'm going to drop the idea of a reference angle, because I'm assuming it's in quadrant 1. I'm just going to take the inverse cosine of 0.8320, and I will know what the sum of angle A and B is. It doesn't matter which mode you're in as long as you're in the same mode for all of these calculations I'm going to show you, but I think if we're in degrees it might make more sense. Okay? And I'm thinking ahead here, and I think it might be the case that maybe we're going to end up outside of quadrant 1, but don't worry about it. It's going to work. So I take the inverse cos of 0.8320, and I get this number. Now that's A plus B, and I want to keep all the decimals. So I'm going to have to organize my thoughts here. A plus B is that number 33.695. Degrees, and I'm going to store that as letter D. I'm just going to store it in my calculator, so I know some of you are good at just scrolling up and grabbing different numbers. I'm going to store it as D. Just because that's a letter. I don't know why I'm using D. Actually, no, never mind. It doesn't. The D doesn't stand for anything. It's just D. I just need to know which letter I've stored it as. Now I'm going to take the inverse cosine of 0.4358 to determine what A minus B is. And as I said, this is a lot of number crunching to keep organized in your head, 0.4358. So it's 64.16. I'm going to store that as E, just because. So I started this explanation off when you first asked about the question by saying, most people are going to try to find A and B, and I said, you don't need to. Well, I am. Because now I have a system of equations that has A and B in it, and it's set up very nicely that if I add them, then I'm going to get 2A equals whatever the sum of these two numbers is, which is D plus E. Which is D plus E. So this 97.859 is 2A, and now all of a sudden I can divide that by 2. I know angle A. This is a lot of number crunching, but some people will be successful with this. I know angle A. Well, why don't I just pop it into angle A? I don't know if I need to do that to finish the question. Now, how do I find angle B? If I want to carry all my decimals, I can take D and subtract A to get B. So this stuff I've written here where I'm storing these things as D and E is important because you don't want to rely on your memory. Oh, where did I put that? So if I take D and subtract angle A, I have B. So this is what I thought would happen. We end up with an angle that's not in quadrant 1. That's okay. Don't worry about it. Now we know angle B. What were we asked to find? I'm going to store this as B. We were asked to find cos A, cos B. Okay. That is exactly half of that 1.2678. It's a very long-winded way of doing it, but it can be done that way. Anyways, Abby, does that do it for you? Is that okay? Other questions? Go ahead.
8C.
C? This one?
Yes.
Okay. Now keep in mind, and I'm going to go through this, keep in mind I didn't actually assign 8. I'm not criticizing you for asking about it. Because technically, number 8, does it say prove?
Yes.
Okay, so we haven't officially done proofs, but I think this is a good mental exercise for us. What we want to do is prove that the left side and the right side here are equal to each other. And when you do a proof, you work on the left side and the right side independent of one another, which means you really drop the equal sign. And you use your mathematical prowess to either turn the left-hand side of this into the right-hand side, or you use all the tools at your disposal to turn the right-hand side into the left-hand side, or maybe you work on both sides separately and find a middle ground. I don't think there's really much we can do with this. I am aware that you can factor this right-hand side as a difference of squares, but I would rather not. What I'm going to do instead is apply a known identity to each of these pieces. For example, the sine of x plus y is going to be sine of x cos of y plus cos of x sine of y. Does that make sense?
You put x.
Thank you. this other piece is going to be, sorry, I'm thinking ahead here about what's going to happen, and I shouldn't be doing that. Sine of x, cos of y. Interesting. Minus cos of x, sine of y. And these two things are conjugates of each other. So if we FOIL this out, we're going to get a difference of squares. I'm not sure where this is going to go. Just give me a second. Well, let's FOIL it out and see what happens. I have a feeling I know what we're going to have to do, but I have to see the next step. When I FOIL this out, there it is. I'm going to have to multiply the sine of x cos of y times the sine of x cos of y. This is going to be a bit of a beast. And I'm going to get sine squared of x cos squared of y. I'm not going to write this out. I hope that everybody sees that my inner product, the product of these two things, and my outer product, the product of these two things, will be equal but opposite. I'm going to get, for my inner, what a mess, cos x, sine x, cos y, sine y. And for my outer, I'm going to get negative cos x, sine x, cos y, sine y. So the only other thing I have left is the last, which is minus cos x sine y times cos x sine y, which will give us cos squared x sine squared y. That look good? Okay. And it's at this point that you're walking down that road and you go, oh man, I think maybe I made a mistake. But I don't think there's anything else we could have done. One of the things you will notice is that in the right-hand side, there's no cosines. There are no cosines in what we are trying to make the left side equal to. When I give you a sheet that will be very similar to the pink sheet that talks about proofs, there will be one more item, and the other item will be always keep your eye on the side of the proof you're not working on. So here I'm saying we're going to keep our eye on the right-hand side, and since there is no cosine, I'm going to get rid of my coses. And I'm going to get rid of my cos squared of y by putting in 1 minus sine squared of y. Because, let me highlight this for you. These two things are equal because 1 equals cos squared theta plus sine squared theta. So that's one of those many variations of the identity cos squared plus sine squared equals 1 that I've highlighted here that I've asked you to try to remember. I don't see right away, everybody, how this is going to turn into the right-hand side, but I'm thinking it has to because we're getting rid of the coses. Okay? And then over here, for the cos squared of x, I am going to put in 1 minus sine squared of x. And then I'm multiplying by sine squared of y. And I see right away it's going to be working. You don't have to see right away that this is going to work. But now my stress level just went down again. Because as soon as I started expanding this to here, Ryan and everybody, my stress level went up. And I'm not having some kind of deep confession with you. I'm telling you that's natural. It's like I'm walking down that road and it got really, really dark and I just plowed ahead a couple more steps and the light is starting to come out. When I expand this, I'm going to get sine squared of x minus sine squared of x sine squared of y. When I expand the next one, now be careful here, I have negative 1 times sine squared of y times 1, which is negative sine squared of y. And then I have sine squared of y times negative 1 times negative sine squared of x, which gives me positive sine squared of x sine squared of y. And it's not that they're really canceling, it's a difference, and I don't like to use the word canceling for difference, but negative sine squared x sine squared y and positive sine squared x sine squared y are 0, and I'm left with sine squared x minus sine squared y, which I hope was what we were trying to do. Good? Yes, Jason?
Question
3? Okay. So it doesn't really matter which one we do. Do you have a preference, A or B? Okay. Okay. So I'm going to go with B only because it has radians, and that's maybe a little more challenging. We do have to think in terms of degrees. So the first thing I would recommend is taking 180 degrees divided by 12 to find out what that angle is. And I believe that's 15 degrees. So we are asked to find the cosine. Well, you know, we're not asked to find the cosine of 15 degrees. We're asked to show that the cosine of 15 degrees is equal to the square root of 6 plus the square root of 2 all over 4. So in my mind, this is how it works for me, is I just say to myself, let's find out what it is, and hopefully we get that answer. I have to rewrite this as a sum or difference of two angles from the unit circle that I'm familiar with the coordinates of. Okay, now 15 degrees is on the unit circle, but we don't know the x and the y coordinates, so it's kind of a waste of time. So what two angles add or subtract to get 15? Whenever you do these problems, the angle you're working with will typically end in 5, which means 45 degrees is involved somehow. And with a little bit of thought, we see that it's 60 degrees minus 45 degrees. And both of those angles, 60 degrees and 45 degrees, are angles that, I mean, all angles are on the unit circle, but they are angles whose coordinates of intersection points on the unit circle we know. We should know that at 60 degrees, the x coordinate is 1/2 and the y coordinate is root 3 over 2. And if you don't know that, this is where you can weasel and maneuver your way around the unit circle by cheating on your calculator and going, well, cosine of 60. Oh, 0.866. That's root, no, 0.5. Cos is 0.5. Yeah. So you put in cos of 60 in your calculator, you see it's 0.5. You put in sine of 60 and you see it's 0.866, and hopefully you recognize that's root 3 over 2. Anyway, what we're going to do here, Jason, is we're going to write this as cosine of 60 degrees, cosine of 45 degrees, plus sine of 60 degrees. I could teach to be 100. I'll always run out of room at the end of the board. Sine of 45 degrees. So I'm applying the difference identity for cosine. And then I go to my knowledge from the unit circle, or from the last unit really. Cos of 60 is 1/2. Cos of 45 is root 2 over 2. Sine of 60 is root 3 over 2. Sine of 45 is the y coordinate at 45 degrees. At 45 degrees, the x and the y coordinates are the same, so sine and cosine of 45 are both the same. So BEDMAS says we're going to do our multiplication, which is here and here, before we worry about addition. I multiply two fractions by multiplying across the top, giving me root 2, multiplying across the bottom, giving me 4. Over here, when I multiply root 3 by root 2, I get root 6. That's how radicals work. Over 2 times 2 is 4. We have a common denominator, so when we put them together, they will both be over 4, which is what we were asked to show cos of 15 is equal to. Is that good? Good. Perfect. One final question before we move on. Go ahead, JV. 4b? So cosecant, okay, I'm glad you asked about this because it's not sine or cosine. We don't have a sum or difference identity for cosecant. The first thing that you need to understand is that cosecant of 105 degrees, there's all kinds of ways to think about this, but this is what goes on in my mind. It's the same as, I could have just written equals, but I want to just write it in words. It's the same as the reciprocal of sine of 105 degrees. Okay? So my thinking here is we're going to find sine of 105 degrees. I'm going to imagine it's asking me, what is the sine of 105 degrees? And then I'm going to take whatever I get and I'm going to flip it over, and that will be the answer to the question. So remember, what I am working on here, which is the sine of 105 degrees, is not the answer to the question. I need to do one more thing afterwards. But it is sine of 60 plus 45 degrees as a quantity for the argument. Right? So we break up 105 into two familiar angles. The sum identity for sine says we have to take sine of 60 degrees, cosine of 45 degrees, and add cosine of 60 degrees, sine of 45 degrees. Did I get that right, JV? I just want to make sure. And if I were, just like when I'm teaching, I want to make sure it's right. If I were writing an exam, I'd look at the formula sheet just to make sure, no matter how many times I think I know it. Just to shave a bit of time off here, because I think I know where the big bulk of this question is coming from. I'm not going to explain how we get these. Sine of 60 degrees is root 3 over 2. Cos of 45 is root 2 over 2. Cos of 60 is 1/2. Sine of 45 is root 2 over 2. In fact, this is almost identical to what we did before. And we put this all together, and you get root 6 plus root 2 over 4. And that is the sine. That is the sine of 105 degrees. So the cosecant of 105 degrees is equal to the reciprocal of this. And I'm going to go out on a limb and say that that's not the answer they have in the back. Is that right? Or do they have this? Okay, they have this though, right? Okay, let's not worry about the other one. So if you're looking at the other one, there is something that we could do here, which is to rationalize the denominator of this, which you learned last year, and it's just, I don't want to, it's not important at this level. Is that okay? Okay. If we had a little bit more time, I would. And maybe I will after the lesson. By the way, this lesson that we're going to start now is very short. Most of the work involved in this lesson is going to be you practicing. We're looking at Part II of Section 6.2. 6.2 covers the sum identities, the difference identities, and something called the double angle identities. So we're looking today at the double angle identities. And I really only have one type of problem that we're going to be doing with the double angle identities. And I will show you how you can do them on your calculator as well, as opposed to using an identity. Here they are. So let's just talk about these individually. The sine of 2 times an angle is always the same as 2 times the sine of the angle times the cosine of the angle. What does that even mean? It means, if I want to just pick an example here, sine of 30 degrees. Well, 30 degrees is 2 times 15 degrees, which means I should be able to just take 2 times the sine of 15 degrees times the cosine of 15 degrees and get the same thing as the sine of 2a, the sine of 30. You know, we run into this thing, we had a little conversation yesterday. Why all these identities? Where are we ever going to use them? You're going to use them at higher levels of math. And by choosing to take Math 30-1, you've started walking down that path in your mathematics education. So just to verify this to you, or with you, I think I'm still in degree mode. I am. If I take the sine of 30 degrees, I don't know why I actually entered it. I know it's 0.5. But if I take the sine of 15, which is it would be some weird decimal. Same with cos of 15. But I take 2 times the sine of 15 degrees times the cosine of 15 degrees, even though sine of 15 is some irrational number, and cosine of 15 is some irrational number, you get 0.5. So I'm not going to verify all of these. I just need you to understand, and this is maybe the best way I can think of to put it, that these two things are the same things. They just appear differently. It's no different, this is true for any identity, it's no different than writing x plus y and then quantity squared, and then writing x squared plus 2xy plus y squared. These are the same. The fact that you've written them in different forms is not relevant. Now, you'll notice that there's one double angle identity for sine, there's one double angle identity for tangent, but there are 3 for cosine. Well, if you take this first identity for cosine, which, by the way, do not confuse cos squared of an angle minus sine squared of an angle, which is equal to cos of 2 times that angle. Don't confuse that with this Pythagorean identity. It's different. But if I want to, I can take this and put it in here. Nope. And put it in here. Because sine squared of alpha equals 1 minus cos squared of alpha. And what I would get is cos of 2 alpha, or 2 theta, or whatever you want to call it, is equal to cos squared of that angle minus this thing, which is 1 minus cos squared. And I would end up with cosine of 2 times the angle equals cos squared minus negative cos squared. That's 2 of them. It's like having a dollar minus a negative dollar. You get $2 minus 1. So there's, and this is actually on your formula sheet, there's a different appearance to the double angle identity for cosine. And if I were to replace cos squared with 1 minus sine squared and do the same kind of thing, I would discover that cos of 2 theta is 1 minus 2 sine squared theta. So there's different variations. Let's take a look now at where we would apply this. To begin with, we're going to be looking at proofs eventually, but number 1, write each expression as a single trigonometric ratio. This is a fluke. I didn't mean to use this example when we were just talking about it. It's sine of 30 degrees. It's sine of 2 times 30 degrees because 2 sine theta cos theta equals sine of 2 theta. This is very similar to the warm-up examples from yesterday. What we're doing is we're looking for an identity that kind of has the same pattern as what's in the question. That's all. B, 1 minus 2 sine squared of 20. That's 20 radians, by the way. Well, can you find an identity that has 1 minus 2 sine squared of an angle? The identity is cos of 2 theta is equal to 1 minus 2 sine squared theta. So when we compare 1 minus 2 sine squared theta to 1 minus 2 sine squared 20, theta is 20. Which means, if this is equal to cos of 2 times theta, it's equal to cos of 2 times 20. It's equal to cos of 40 radians. Nothing really difficult with this first set of examples. Once again, you're looking on your formula sheet for an identity that fits the pattern in the question. Okay, so is there an identity that has 2 tangent of an angle over 1 minus 2 tan squared? I got to check something here. That doesn't seem right to me. But I'm no good with my tangent identities. I can't remember them. That's not it. Yeah, there should not be a 2 in front of the tan squared in this question. Do you have a 2 in front of the tan squared, or did I already remove it? So my question to you is this 2 in your handout? It's not. I already removed it. I just didn't remove it from here. Okay. So that's the question in your handout. Okay. So is there an identity that has 2 tangent of theta on the top and 1 minus tan squared of theta on the bottom? Yes. Tangent of 2 theta. So if this is equal to tangent of 2 theta, then it's equal to tangent of 2 times pi over 12, or tangent of pi over 6, which, since pi over 6 is on the unit circle, I suppose we could spend some time finding it, but I don't care to. That's not the point. All right. Angle A is in quadrant 3 and tangent of A is 5 over 4. What's sine of 2 times A? Well, this is very similar to what we did yesterday with, I hope you remember we had that big, long, complicated problem that I botched the final part of it with, but we had angle X and angle Y, right? Remember that? And they each had an X, Y, and R. This is even easier because all we have is one angle, angle A. We need to know X, Y, and R. The reason you need to know X, Y, and R is sine of 2A is 2 sine A cos A. So we're going to have 2 times Y over R times X over R. We just need to go back to unit 3, the previous unit, and use our skills to determine what X, Y, and R are equal to. So I keep throwing this kind of trick question at you. It's probably 5-6 times already you've seen it, where you might make the mistake of saying, since tangent of an angle is y over x, y must be 5 and x must be 14, but it's in quadrant 3, which means x and y are both negative, right? You've seen that a dozen times is maybe an exaggeration. We've seen it a lot. Let's calculate r. Now don't forget, if r happens to be a rational number, then we should roll with it. But if r squared is an unperfect square, we have to put the square root of that number as r. And it turns out it's not really going to matter. You'll see why in a second. The 221? 221 is not a perfect square, is it? No. So r is equal to the square root of 221. All we're doing here is we're taking negative 14 squared plus quantity negative 5 squared equals r squared, and you get r squared equals 221. And that means, and here's why it really doesn't matter about the radical. We're going to have 2 times y, which is negative 5 over r, root 221, times x, which is negative 14 over root 221, And the root 221 times the root 221 is going to give you 221. Right? The square root of a number times the square root of the same number will give you that number. So we end up with, I believe it's going to be 140 on the top over 221. 2 times 5 is 10. 10 times 14 is 140. And then over 221. 221 is a weird number in my head. I don't know. Is it prime? Like, does it even, are there any factors of 221? I don't think so. Anyway, I'm pretty sure 140 over 221 doesn't reduce any further. The nice thing about this, everybody, is we now know x, y, and r. So to answer question B, we're just going to roll with those x, y's, and r's. So maybe you want to do this. Cos squared of A minus sine squared of A. Remember, I'm going to need somebody to confirm here. I'm pretty sure these were the values of x, y, and r. Yes. So cos is x over r. Sine is y over r. So we would take negative 14 over root 221 squared minus negative 5 over root 221 squared. Well, those brackets are pretty important. When you square negative 14, I know you guys want to use your calculator and throw the whole thing in, but I want to try to convince you not to. Negative 14 squared is 196. You can certainly use your calculator to find out what 14 squared is. But I hope, well, actually what I hope is when you square negative 14 on your calculator, I hope you don't even put the negative in, because you know it's going to be positive. If you do put the negative, you need brackets. When you square a square root, those two operations are inverse operations. They cancel. We'll have minus. Then we have 25 over 221. We're fortunate enough to get a common denominator. So you end up with 196 minus 25 all over 221, which means cosine of 2a is equal to, how's my subtraction? 171 over 221. If you wanted instead to use 1 minus 2 sine squared a, then you would have 1 minus 2, and I don't think you need to write this down, times sine of a quantity squared, which is negative 5 over root 221 squared. You would end up with 1 minus 50 over 221, because the 5 squared is 25 times the 2 is 50. If you convert the number 1 to a denominator of 221, you're going to get 221 over 221 minus 50 over 221. You're going to get 196 over 221, or 171 over 221. You can use either identity. And then we'll do tangent. Now we're going to do what I wanted to do yesterday. I don't think we really need to use the tangent formula. I don't even remember what it is. That's how rare or how infrequently I use it. So 2 tan a over 1 minus tan squared. You could do that, and I'll leave it to you as an exercise to do if you want. But we know tangent is sine over cosine. And since these angles are the same, we can do that. They weren't yesterday. That was my mistake. I used x minus y in my notes and x plus y in my notes in two different places. So sine of 2a, I got to go back and take a look. Sine of 2a was 140 over 221. Over cosine of A was 171 over 221. Did I get those two trigonometric ratios correctly? Correct? Okay. So again, you could, multiply by the reciprocal. I prefer a more general approach here, which is to multiply the top and the bottom by 221. What's going to happen is the 221s will cancel in both cases, on the top and the bottom, in other words, and you will get 140 over 171. Any questions with that set of examples? Now, I don't like multiple choice questions that you could do on your calculator, but the diploma exam sometimes has a question like this as a multiple choice question. And even if it were numerical response, we could still cheat. You understand, I mean legitimately cheat. And do the following. So, it tells me that it's in quadrant 3, and it tells me the tangent. I can find the angle. I could find the angle quite easily. I would find a reference angle by taking inverse tangent of 5/14. I'm in degrees, so I can make sense of it. If I'm in radians, it's 19.65 degrees. My brain can cope with that. If I were in radians, and I repeated that, and I got 0.343 radians, my brain is kind of losing interest already. It doesn't really make sense to me. So you want to be in degrees when you try this. So we'll do that again. Inverse tan of 5 over 14. That's the reference angle. If it's in quadrant 3, this is 19 degrees. The rotation angle, which is actually A, is 180 plus the reference angle. So I'm going to add 180. That's angle A. That's angle A. Now, we want to be very careful about something here. I'll save this. I'll save what I'm about to say for a minute. I'm just going to store it as A because I want to use this number multiple times. So what is the sine of 2A? Take 2 times A, which is that, and take the sine of it. And convert it to a fraction. Bob's your uncle. 140 over 221. What is the cosine of 2A? Well, I'll take the cosine of 2A. I mean, really, as a time saver on an exam, if we're going to give you a question that could be done on your calculator, why not? And I mean, this does show some level of understanding of trigonometry. You have to work with quadrants. And what's tangent of 2A? Was tangent of 2A the same as sine of 2A? Oh, no, it's over 171, not 221. That's what we got for tangent. I want to point something out to you, and every time I teach this course, when I give the unit exam, students get this kind of question wrong. Okay, and here's what they do. I'll use cosine as an example. They do all this work, and they get this number, okay? And that's a choice, along with some other things. So one of the choices is 171 over 221. One is negative 171 over 221. One is whatever. And a student does this. And I can almost watch them doing this and know exactly what they're thinking. And they go, oh, no, it's got to be B. And they circle B. Because they're saying it's in quadrant 3. Does that make sense? So they're saying it's in quadrant 3, so they're assuming they've made some kind of numerical mistake, and it's actually negative. But its angle A is in quadrant 3. This is the cosine of 2A. Who knows where 2A is? So you cannot look at the original quadrant and make that decision. You have to go with the math. The math says cosine of 2A is positive. By the way, A was 199 degrees. That is definitely in quadrant 3. (399 is actually back in quadrant 1, isn't it? So don't make that mistake. The first couple times I taught this, I was baffled because I would see people, you know me, I just get you to circle it. I want to see your work. I would see people and they would have this as an answer, and then they would circle the negative one. And it finally dawned on me that's what people are thinking. Anyway, that's the lesson. On page 14 of the handout, 1 to 4, and on page 306, 5, 10, and 11 of the text. Some supplemental problems there as well at the end of the unit if you're interested. So you got about 20, 25 minutes here. You got about 25 minutes here, I think, to work on this. And I just want to take attendance and do one more thing, and then I will come around and I'll give you a hand.